I mean, have anyone heard of partial fractions by any chance? Ever before? But I'm sure that you know, sometimes you have to either add or subtract fractions, right? So I know that people don't like to call things that you see over here fractions, right? But I hope that you're open to the fact that they are fractions, right? It's just that you don't know what x is, and that makes them rational expressions, okay? Now, let's see. That's kind of weird. Let me just put something on the OneNote so then I don't have to go back and forth between the two whiteboards. How do you figure it out? The math behind subtracting, say, 3/2 and 4/3. And you know, I just make these two random fractions. How do you do that, Ariel? What would that be? 6, right? Everybody sees that. It's basically multiplying 2 and a 3, right? Now, I think that not everyone, including myself, will, you know, seriously write down a lot of work. But at least that for the sake of 8.3, I suggest you think that the reason why you're able to subtract the two fractions with different denominators is you figure that you could rewrite the first fraction by multiplying both the numerator and denominator with a 3, and that's not a random number, it's the other factor right there, right? It's the other denominator, because you know that 2 times 3 gets you the least common denominator. You can rewrite the second fraction the same way, but multiplying whatever factor you need, which is actually the other denominator, right? But to both the numerator and denominator to get both fractions over the same denominator, and you can go ahead and subtract the numerator, right? So that will be 9 minus 8, so 1/6. Okay. Now, as you go from the two fractions subtract each other to a simple result, that's called subtraction of fractions. Okay? But now, what if I provide you 1/6? I'm asking you to find me two fractions who subtract and get you 1/6. And I want you to be able to do that systematically. So you should follow some rule, right? To always find two fractions, even more than two fractions. But I want a whole bunch of fractions, which add or subtract gives you that single fraction at the end. Right? And that process is called partial fraction decomposition. Okay. Now, do you see that the process of going from a whole bunch of fractions adding subtracting to a single fraction should be the same, or the idea behind it should be the same as you going from a single fraction, break it down into multiple fractions? Do you think that algebraically, you know, they should work out the same way? Right? It's like, you know, if you know how to get here from your home, do you know how to go back? Yeah, just, you know, I mean, you can take some shortcut, right? But the worst case scenario is to follow the same route back, right? But, well, guess what? A lot of the things or process in the math, since we're so used to going one way, then if I ask you to go the same way back, it might not be as straightforward as it seems. Okay, and that's why people get thrown off right away because they thought that, well, how am I supposed to go back? You know, if there's so many different options out there, do I just keep guessing, right? And that's why I said we need a way to systematically get you, you know, possible fractions, and you can check to see if it works. Okay, but I guess that later on, as you will see, you're not really dealing with a whole lot of you know, complicated algebra, even though it seems to be the case, but it's really not. At least that if you tried the first, I'll say 5, 6, 7, 8 questions, on a packet. Not to mention there are multiple choices. There are ways that, as long as you understand what you're trying to do, finding the answer is not going to be as lengthy as you thought, or even compared to the work that I provided you. Okay. Anyway, now let's make sure that we address those things properly. Now, from now on, at least in A3, you'll be given a rational expression, right, or quote-unquote fraction. So you want to break it down into a couple more fractions, right? They are either added or subtracted. So the things on the right, so those guys are known as partial fractions because they are part of the original single fraction, right? And also, do you see that they're supposed to be simpler in a way that you have lower degrees in the denominator? Now, here's the thing. Do you guys still remember what a degree of a polynomial is? Who can tell me what is a degree of a polynomial? Zach. It's the highest power, right? The highest exponent. Therefore, what's the degree of this factor x plus 1? 1, right? Or we call it a linear factor, right? Or a linear binomial, since it has two terms. And the reason why it's a factor is, do you see that originally x plus 1 was multiplied by something else, right? Numbers who multiply get you something else. Those numbers who are multiplying each other is called factor. Then what about the original denominator? What's the degree of it? 2. You see that, if you fill, if you avoid it, right? Or you can tell that the 2x's at the end. Okay. Now, in 8.3, we're doing partial fraction decomposition, and it will only work when the numerator has a lower degree than the denominator. Okay. And the reason why I have to emphasize that is in 3 point something, if you remember, I just showed you the pacing guide. You could do something called long division when the numerator has the same or even higher degree than the denominator. Okay, so make sure that you know when to do long division or when to do the partial fraction. Okay. Now, let me ask you to take a close look at rule number 1 and number 2, either on a packet, or if you want to just look up, and I have it over here, right? So those two rules, just stare at them for like a minute, and I want you to tell me any differences between these two rules, and also any similarities. By rules, I mean, do you see that it's breaking up a complicated but still compact single fraction, right, into a whole bunch of partial fractions? And you're going to use them as formulas, right, which means that you have to remember them. But those two rules, right, just tell me if you notice any differences and similarities. Yeah. Oh, sure. No. I do have extra copies. I don't know if I print out more. All right, so anyone would like to share with us? Notice any differences? I think differences are probably easy to tell since they look very different, right? As I can describe, what the differences are, I'll try to be a little bit more professional, referring to those terms. And Rosalind? Uh-huh. Mm-hmm. Okay. Yeah. I mean, you're not wrong. You notice that we have some superscripts, right, which represent a power, but some subscripts representing you know, different part of, you know, the original denominator, stuff like that. Now, since she's pointing out the denominators on the right-hand side for both rules, right? Do you notice that there's something that keeps appearing in the second rule? X plus b, right? That's a linear factor. Gets repeated for n times, right, in the multiplication. And somehow, on the right-hand side, it shows up how many fractions? There are actually n fractions, because the first power, second power, nth power. So there are n fractions, and each fraction takes the same linear factor as its denominator, but raised to the appropriate power, right? It's like the 10th term, the 10th fraction has the same factor raised to the 10th power, okay? But what about the numerator, or the denominators on the right-hand side of the first rule? So these guys, I mean, should we expect that they should be exactly the same as each other? Like this, the a sub 1, a sub 2? No, right? So otherwise, you know, why would I call it, you know, differently? It means we're not looking at how many linear factors that are multiplying each other out. There are still n linear factors, right? And they are supposed to be different, right? Or potentially, right? You shouldn't expect they're the same. So you have n distinct or different linear factors, and each one of them serves as a denominator of a partial fraction, where the second rule says it is the same factor you keep taking as the denominator, but you have to raise it to the power, right? Whatever power you think is appropriate. So that's the difference, right? I know that's, you know, the mouthful of a difference, but what about similarities? Anything that you notice they're kind of the same. The numerator is on the right-hand side, right? So even though there are some coefficients and constants we have to determine, right? And that's the whole process of, you know, the partial fraction decomposition. But at least that, you see, even if sometimes you have things as complicated as something to the nth power, but the numerators are all numbers, right? And it turns out that every single fraction has just a number, right, as the numerator. Okay. Yeah, that's actually pretty good. And the reason why I have to emphasize that you have to see anything that are similar and different is you need to pick from one of those four or even a couple of rules and apply them at the same time. So you have to find out the correct one. So now you know they're similar in a way, but they're also different because they're addressing different scenarios. Now, what about rule 3 and 4? Well, I have to zoom out a little bit. Now, do you see that you have the same pattern, right, when it comes to whether the factor is repeated for a certain number of times, right? But in this case, you see that ax squared plus bx plus c is not linear anymore. It's quadratic, right? A quadratic factor repeated for n times, so you need n partial fractions. Each of them takes the same factor, but raised to the power up to n. Or rule number 3, you have n distinct quadratic factors, right? Each of them serves as a denominator for a single fraction. Okay. Now, I think that you can even think about writing your own rule in the future if you need, but you never have to do that because you see that the process ends at the rule number 4 because there's no point of doing it since things are pretty repetitive. But you can guess. If I were to put down rule number 5, rule number 6, they'll be addressing what kind of factors in the denominator? It will be, would you say cubic factor? Since rule number 1 and 2 are about linear factors, right? 3 and 4 are about quadratic factors. Rule 6, 5 and 6 will be, you know, cubic factors, right? Now, what about the numerators? We have a sub 1 x plus b sub 1, a sub 2 x plus b sub 2, right? The same thing here for the rule number 3 and number 4. But you notice that things get more complicated if you deal with quadratic factors in the denominator, because the numerator must be up to the first power. Now, it's good to understand that you're only supposed to do partial fraction decomposition if the numerator you start with is at least 1 degree lower than the denominator. And as you're getting those partial fractions, then whatever you put on the numerator is supposed to be at least 1 degree lower than the factors on the denominator. If it's quadratic, then you have to be open up to the first power. Okay. Now, let's try to use at least the first rule, which is actually the most classic one. So if you're able to use it and quickly get the correct answer for maybe some of the easy questions on the test review packet, I'm sure that you already mastered the skill of using the partial fraction decomposition. It's just that there's some subtle scenarios involving some algebra that you have to deal with, which is going to be a little bit easier to deal with as long as you know what you're trying to do with rule number 1. Okay. All right. So now in the next couple minutes, please make sure that follow the algebra for letter A on the packet, and hopefully tonight you'll find either letter B on the packet or maybe the first couple questions on a test review packet to try the same skill that I'm showing you right here. Okay. So letter A belongs to case number 1, and there will be 4 cases, just so you know. That's why I'll spend the class tomorrow to work out all those cases. But case number 1, the easiest one, the denominator that you're starting with is a product of distinct linear factors. Okay, you can see that the 2 factors, x minus 4, x plus 2, they are different, and both of them are linear. So we will apply the rule number 1 by assuming the schematic form of the partial fraction decomposition is some constant a sub 1 over x minus 4 plus some other constant a sub 2 over x plus 2. Okay? And your goal is to find out what those 2 constants, a sub 1, a sub 2 are. Now, do you realize that you're pretty much dealing with a rational equation, right? I believe that the best way to deal with rational equation is to get rid of the denominators. Okay, and you could do that by multiply both sides with the least common denominator. And can anyone tell me what the least common denominator might be? Think about what we did with the number. What, x plus 2? Anything else? X minus 4, and they are just multiplying each other out, right? So it's just multiplying 2 and a 3, right, to get a 6. And yes, you just take the product of these 2. Now, do you notice that it shouldn't be anything hard at all, because that's indeed exactly what the denominator you started with in the first place. Do you see that? So no need to think about what the LCD is. It is right there. So now let me go ahead and multiply the left-hand side with x plus 2, x minus 4. Now on the right-hand side, we do the same thing. Okay, so on the right-hand side, well, on the left-hand side, it's trivial because, it's supposed to cancel the entire denominator. You're left with just the numerator, x minus 14, right? On the right-hand side, just be careful that you have to distribute that LCD. And if it hits the first fraction, do you see that the denominator x minus 4 get crossed out? You're left with only a1 times x plus 2, right? The factor that survived. Now the second fraction becomes a sub 2, right? But instead of x minus 4 got crossed out, it is now x plus 2 get crossed out. You're left with x minus 4, right? But still multiplying a sub 2. And that equation, once you get rid of all the denominators, is known as the master equation. Okay? So now you're going to play around with any numbers of x you want to get yourself an easier life, so you can find out a sub 1, a sub 2 without doing some crazy algebra. For example, what if I take x to be 4? So I can evaluate the left-hand side, right? 4 minus, oh, sorry. Yeah, thank you. Yeah, 4 plus 14. What about the right-hand side? First part, a1 times 4 plus 2. What about the second part? X is 4. Should we just get a 0? Right? And now, do you see why I came up with a 4? So it kills the second part without even me knowing what a sub 2 is. Now you can solve for a sub 1, which is, well, you know what? Let me write down the number. So 18 equals 6 times a1, right? Therefore, a1 must be 3. So now, can you guys come up with some other x value? So I can kill the first part and find out what the a2 is. What do you want to take the x to be? Negative 2. Good, right? So now on the left-hand side, it's negative 2 plus 14. On the right-hand side, you get a big fat 0, right? And a2 times negative 2 minus 4. You get 12 equals negative 6 times a2. And a2 is negative 2, right? Therefore, you can conclude that the original fraction, x plus 14, over x plus 4, x minus 4, x plus 2, can be now written as 3 over x minus 4 plus negative 2 over x plus 2. But some people don't like to have the negative 2 on the numerator. They'll write it as 3 over x minus 4 minus 2 over x plus 2, right? And this is the partial fraction decomposition we're looking for, okay? That's it.